is this area just in front of us, and you can see these lines like these. These are all shear bands from everything forcing its way up, and basically this little inset box here, which is showing carphalite. It's just in here somewhere. You can use your handouts to try and locate it. So yeah, what should I tell you? So the Rui unit is bounded by the Yenkit shear zone and by the Wadi Kanu fault. I mean, we've got it behind that pale and up over there, and this is Horwicina just here, just draping on there. But anyway, and exhumation related to shear. Carphalite bearing quartz-rich boudins are preserved within the shear bands. So let's come and see if I can find this.
Oh, that one.
Hillary?
It's a rare manganese silicate rock mineral. It comes in radiating clusters. It is orthorhombic.
That's the picture.
So,
Some in these quartz boudins, it says.
It's a low-grade metamorphism,
Really
see?
need a thin section.
It might have been collected as well, of course.
Yeah. But it's actually a low grade.
Carphalite is a rare manganese aluminum silicate mineral. Distinctive yellow fibrous and radiated crystal structures. Low-grade metamorphic rocks. These look like they're mudstones that have been slightly metamorphosed and are all deformed.
Where?
Yeah. See?
Well, you know, when you do it at 100 miles an hour.
Oh, sorry.
Okay, let me take it again.
Here, have a pick.
Okay.
Have a clean fingernail.
Good. That's just what I needed. Thank you.
The quartz veining will respond differently to the shearing compared to this more fine-grained stuff, so it will break. You see, it's a beautiful example there. You see the net. This could all be the last.
So we're in the last day of our trip. We're just east of Muscat, and if we understand this diagram completely, or when we understand, so we're in the last day of our trip, and we're just east of Muscat, and this very simplified diagram explains it all, and when we understand it, we will understand the complexity of the abduction. And today's stops are marked here. So right now we're in the melange, the Rui melange. It's a mudstone. We'll take a look at it. It's slightly metamorphosed, highly deformed. And in the big picture, what's happening is the rocks here are being forced below the rocks here, but they want to rebound. They are too light and they do not want to subduct. So they're going down, but then they're rebounding. And so there's a tremendous amount of shear here. And so for today, we're going to see examples within the fault zone that we're in now, the melange. We're going to see a couple other stops within the deformation, the very significant folds, horizontal folding, because as things are going down and getting dragged, there's a tremendous amount of shear. And then we're going to look at the Eocene, Eocene ophiolite contact, which is an angular unconformity. So it's going to be a pretty exciting day, and this diagram is really fantastic. And just for a second, this is a cross section. Every cross section needs to be plotted on a map. So here is the cross section that we're looking at, and so the stops that we're looking at are all up in here today.
In a nutshell, I'll say the simplified thing first of all. We're looking at the subduction zone. Boom, here it is. This is the continental margin. It's diving down, and here's the ophiolite. And you're looking at that, and then after this was all in place, this Eocene rock was deposited on top as an unconformity. That's the simple story, and you're seeing how Muscat is constrained by being in these mountains of mantle, and directly the other side of the Mantle Mountains there is Old Muscat, all the city government buildings and the true city centre. and you can see how they're actually cutting away into these mountains to expand the city, which I think is a bit of a shame, to be honest, but it's just showing how the city it constrains it. Now, that story is all basically true. Boom, this is the subduction zone, except for one clarification, and that is some people say that this actually isn't a subduction zone, it's a parallel fault to the subduction zone, and where we started coming up the road, coming up the steep bit there, that's the subduction zone. And if you look on page 47, you can see these two alternative explanations. That one says that, no, this is a subduction zone. The other said, no, that's a subduction zone, and this is just parallel to it, and it's just a sort of little parallel slice. But I think we're nitpicking, really. For the big, impressive photo story, this is the subduction zone, and this is coming down, and you can clearly see how this material has gone underneath the ophiolite. That is the ophiolite, and then we can see once all the ophiolite was in place, things were still marine, and the Eocene got put on top of it, and that's the same Eocene we were seeing in Wadi Shab yesterday, and we were seeing on the coastal notches. There it is, sitting unconformably on top. Okay, so that the exact nature of the Kabir fault is debated. In its present geometry, it behaves as a normal fault, as Eocene limestones that cross the fault are down-thrusted by approximately 150 to 400 meters. So that happens up there, on this northern side. However, two interpretations are proposed. One possibility is that the Kabir fault represents a reactivated segment of the Somail thrust, which originally carried the ophiolite over the Arabian margin and was later reactivated as a normal fault after subduction ceased. So i.e. it is the subduction zone, but it's now been reactivated as a normal fault. Alternatively, the fault may be a separate structure formed independently of the Somail thrust and functioned only as a normal fault throughout its history. This uncertainty highlights the complex transaction from compressional to extensional tectonics. So if it isn't the plate boundary is just where we came up the hill. But this kind of looks more visually appealing to call it this. But anyway. I'm standing on Permian and Triassic age rocks of the continental margin of Arabia, and a subducting slab dragged them down underneath these mountains to our right. These mountains to our right are actually rocks of the mantle, so all this was happening beneath the ocean, and this road is representing a former subduction zone. This was dragged underneath, and here you have all the mountains, as I said. And looking back up this way, there's yellow rock sitting unconformably on top, and that is actually Eocene limestone. So all of this happened in the Cretaceous, but it was still all under the ocean, and then this Eocene limestone was placed on top, still under the ocean. But today it is up in the air forming mountains because Oman is beginning to collide with Iran, and this is uplifting the whole area.
Okay. Welcome to Wadi Kabir, K-A-B-I-R, which means Big Wadi. And what we're looking at is actually absolutely a spectacular panorama. Let me guide you through the subduction zone, and let's look in the far distance where we're seeing the platform carbonates diving down under the road, and this part of Muscat. The road basically marks the subduction zone. How about that? And in the distance are the ophiolites, the Somal ophiolites. You can see their knobby texture. So the ophiolites are trying to abduct. The carbonate platform is trying to subduct right here, right under the village. And the village is less than 50 years old. There's been so much growth here in Muscat. So one can only imagine that this subduction zone probably is a place of tectonic activity, and the habitation has been fairly recent, so they don't have a lot of historical experience with potential earthquakes. And what makes it even more spectacular is in the distance, this is a very profound unconformity. So on top of the ophiolites, there is a contact with Eocene limestones. So as the abduction pushed down, there was a carbonate platform deposited, and it's now rebounded. So now the Eocene, which was once at sea level, is way up high, and it's here. And if we come all the way around the panorama, you can see it in the distance and the ocean out beyond. So this is truly Wadi Al-Kabir, a spectacular panoramic view of a abduction zone. Pushed down, didn't want to go completely, and then rebounded, and later marine deposits on top.
Right, what I want to say, this is Wadi Mer, and it is the same valley that the world's largest mega sheath fold is in, and that's a few miles up there. But this isn't the mega sheath fold. This is not the mega sheath fold. It's a different structure to the mega sheath fold. Now, if you look on our cross section, which I don't know if you've all got your handouts, it's a good day to have your handouts with you today because there's so much complexity. I've marked number 3, and the mega sheath fold is number 4. So it's there's another thrust fold between us and that. But this is the story that this material has been back down the subduction zone, and it's coming back to the surface and folding as it does. Now, on this geological map that I put on the front page for today's activities, it describes the faults as different F1, F2, F3. Well, what did all that mean? And and it goes up to F5. It means different generations of folding. And basically F1 formed during early subduction and deep burial at high pressure conditions. F2, the most important phase, which this phase is and the mega sheath fold is, F2 formed, it produced north-northeast verging regional fold naps and the Wadi Mer mega sheath fold, accommodating the main late Cretaceous exhumation. F3 is basically the F2 getting refolded during continued convergence as stress directions evolved. F4 represents late stage folding linked to dome amplification and uplift, and F5 comprises minor local folds formed during the final cooling and unroofing. I wouldn't bother going into all that normally, but it's just the diagram speaks to this F1, F2, F3, F4, F5. It just means not all the folding happened at the same time. And this happened in the main stage of stuff coming back to the surface. So, you know, we've had our subduction zone started. It's made the ophiolite. Everything's been going under. Basically, the continent here, it reached the subduction zone here, and it went down. And when the slab broke off, it didn't like being down, and it's coming up to the surface. Now, this fold, you can see it's here on this side of the road, and it's here on this side of the road. The same fold. The valley has cut through it, we will. This diagram on the top of page 49 is just kind of showing the whole extent of it. And if you follow the fold hinge, the dotted line comes down, and we are literally just about where the scale is, saying 400 meters. We're just off the diagram. And at this stop we see a large scale north-northeast verging F2 fold as part of the Scythe Hatat fold nap system. Oh, and there's one other thing I need to tell you. Right at the very beginning of the handout, where we've got the general geological map of the whole trip, it shows 2 cross sections, and we turn over, and the 2 cross sections, the early part of the trip was, how the ophiolites come over, the ophiolite and the Haybee and the Horwesina naps came over the top. They've got to write it off, and you've got the margin in the middle. That was our story. But here it's a really very different cross section, and we're dealing with this very complicated looking area here, this area here, and that's all the stuff has gone down. It didn't like it one bit, and when the slab broke off, it's come back, and that's why the cross sections are so different. So Getting back to this description, the folded units belong to the Arabian continental margin sequence, which was previously buried to high pressure conditions during the late Cretaceous subduction beneath the ophiolite bearing upper plate. These F2 structures formed during the main exhumation phase when deeply subducted continental rocks were being brought back towards the surface. I've said all that already. The fold geometry is kilometre scale, and the exhumation of the Scythe-Hatted dome was achieved through a combination of folding and shear, tightly linked in time to the Somile ophiolite emplacement. Okay, well, that's all I need to say. So it's basically incredibly photogenic, isn't it? Look at that. Take pictures, and then we'll be proceeding up this valley to go and look at the mega sheath fold. A complete view, sideways view. And that's what it is. That's what's running up on top. The hip. That came right up around. But we're only seeing about a third of that Z because the rest have been eroded off. Why such a massive fold? Well, that's because all of this material was dragged down a subduction zone under the Somile ophiolite, and it's been folded as it's forced its way back up to the surface after the slab broke up. But here we can beautifully see it. There's the hinge of the fold, the rest has been eroded off, but this wadi and road cuts through the fold, and actually behind the group here we can see also the fold in that side of the valley, and you've actually got a signboard put up there by the Omani government doing some bit to explain the significance of this site. Clark has offered just to add a little explanation to the last stop, and I welcome that, and then I will kick you off into telling you about this stop. So that diagram, where my number 3 was, directly below that there is a black fault, and below that there's another fault, and in between those two faults is the unit that we want to talk about. This is the mega sheath fold. Now, one of the hardest things to get your head around, but if you imagine a tablecloth and you come down and you pinch a bit of the tablecloth and you pull it up, you're making a sheath, rather like the sheath of a sword or a condom perhaps, but I didn't want to write that in the handout because it felt a bit inappropriate. So it is between the two thrust faults. It's forcing its way up. But to add a bit of complexity to that, if you look at my diagram with our sheath fold, it's not just one condom. The unit actually can get several different sheaths on it, and when you cut these sheaths by erosion, you get eyes. And if we look that way, there is one. It is not completely closing off on the right nicely, but it is one. Here is one just behind the building, and in the diagram on page 50 is actually here, but the author has climbed up there on top of the mountain and looked down on it. But what you're seeing, this diagram shows photograph without the eyes, and then with the yellow eyes drawn, and basically you can start to see them. Here's one where the wires are. It's one. There's another one, and if we'll walk down in a minute down to near the water there to be closer to that and get beyond the wires, and then you can look up and you can start to see that there's actually four different eyes. 1, 2, 3, 4, all in this outcrop here. But standing here, I can already see one directly behind the wires, one and one below. I can see two quite well, but there's actually 4 eyes in that cliff surface. And I'll be honest, I don't quite understand how you go from one condom, if you like, to a thing with multiple condoms all on the big one. And I don't know if you can, anyone else can kind of get your head around how that happens. But the diagram on the bottom of page 49 is sort of showing how you've got these 2 faults I've talked about, and is showing how multiple sheaths do form. So I think this diagram at the bottom of page 49 is the best explanation. Okay.
So that has to be really slippery.
That's why I'm not taking us all up there. Well,
So this is a sheath fold.
So you can see more of the eyes coming into play, but of course where the cars were, you could look back and see that other eye. So
Yes, James, could you just hold your hand out and I will adjust so that you are now pointing perfectly to one of the sheep folds. Thank you.
right, I'm just waiting for you. A very impressive fold, which is obviously photogenic, and it is sort of eye candy. And you can see the layers are coming along, actually coming along here, and then turn like that and come around like this. And this is a sub-stop of the stop we stopped at before. Now, I will actually ask people's opinions on this, because this clearly isn't an eye fold. But it clearly is incredibly close to what we just were. So while it's it's obviously a very photogenic fold, I'm not sure if this is somehow like the edge of the sheath. I don't really understand the structure particularly, but it is very photogenic. And it's a very large fold. And if you look further down the valley that way, it does look perhaps like it's an eye continuing that way, perhaps. But anyway, this site is described as being blue schists. Now I'm going to read out what I've written. So the roadside cutting exposes high pressure blue schist facies rocks within the Saif Hatat Dome, formed from deep structural levels of the Arabian continental plate that were subducted beneath the Samal ophiolite plate. So what that means is as the continent was going down, it had all these different layers of stuff. It deep down in that pile, this is protolith, and it's been taken down into the subduction zone, where the minerals get changed. Now, these rocks represent parts of the Arabian margin which were carried at depth during subduction and later returned towards the surface during exhumation. Recent construction has revealed the footwall of a major tectonic discontinuity. What a footwall means, it comes from the Cornish mining. When you were on a fault, you were standing on the footwall and you hung your lantern on the hanging wall in front of you, and it's just relative to what you're standing on, the other side has moved.
And just to confuse you, all those faults were reversible.
Anyway, yes. But anyway, basically, so this is an exceptional exposure. Now the outcrop shows strong foliation and shear fabrics with top to north simple shear along low angle shear zones alternating with lower strain zones containing folded more competent layers. So that's what we're seeing there. Although these are termed blue schist, the rocks here are commonly appearing grey-green rather than blue due to deformation and partial overprinting during uplift. Okay? Well, this is
Here's the blue schist. Look at all this mica.
Put your hand where the blue schist is.
the rock is the whole
I thought it was
Blue schist facing.
Yeah, but it's not.
it's gray or green.
So, can I just... Sedimentary to me, not igneous. And you really need an igneous rock to develop the blue amphibole of the blue schists. That's my understanding, and I just checked with Clark, and that's what he said too. So you know, so that's part of the problem. Is it's gone to blue schist facies. It's gone to the pressure and temperature at which basalts would develop blue amphibole, glaucophane. But these rocks are sedimentary rocks, and therefore they don't have the right chemistry to develop blue amphibole. But it's got some little guys. If you chemically analyze them manually, it might give away the information.
This outcrop is a low-grade metamorphic rock. It's a sedimentary metamorphic rock that has been high pressure in an abduction zone and lower temperature. It's the sedimentary rocks that include sandstones that have now been quartzite, limestones that are now marble, and shales which are now full of lots of mica crystals. The sandstone and the limestone do not chemically alter very much. They mechanically alter. The shale mechanically alters, and it chemically alters because it has many more ions. And what makes this interesting is that this is blue schist facies, which is high pressure, low temperature, but it's a metamorphic sedimentary rock. The other blue schists that are really blue are made from igneous rocks, where there are different minerals that enable basalts, for example, when they become under high pressure temperature, to form blue schist rocks. These are blue schist facies, but they're not blue. And one final thing, this reminds me of my thesis, because I was looking at limestones and I was looking at a shale below a limestone. And as we followed from shallow down into the basin, the limestone didn't alter, but the shales below it altered, just as they do here. And that shale cooked the limestones, affected the limestones above.
Do you think it's lit up at night? Are they just rubbish or lamp?
Already touching dunite. You're already touching magnesite. But I'm going to take the group up higher, maybe to the shelter.
Oh, this is really good.
Yeah, just the half the side is